Speaking of the geometric field, there are some member function whose task is to simplify and update the boundary condition. Okay, so this is the main functionality that we are going to discuss in this tutorial. Now, if you want to update the boundary condition and if you want to simplify the boundary condition, then you need to require the access the adjacent internal cells of the boundary patches. So if you want to update the value, then the adjacent cell which is near to the boundary patches, this cells you need to access, and there will be some calculation that you are going to do if you want to apply some boundary condition. Okay, now let's see that what is the source code of the geometric field. Then we will discuss some more functionality of the geometric field. So let's go to the uh, source code of the geometric field. Here we are in the documentation of the version 6, OpenFOAM 6 documentation. So if I type geometric field, okay, so here you can see that it is the .th file and that is the .c file. So I'm going to open the .h. Okay, so here you can see here that it is has been derived from the various classes, that is the dimension types, dimension field, and there are other classes that you can see here. Okay, now if I go to the and open the definition of the geometric field.h, okay, so you can see that this is the source code file of the header files of the geometric field. Now there are some forward declaration you can find. Okay, so I have told you that why this forward declaration is needed. So you can see that there is a forward declaration, and here the definition of the geometric field has been started. Now you can see that this is the derived from the dimension field. Okay, so you can find that this geometric field definition start with the deriving it from the dimension field. Now speaking of the template, you can find that 3 template is given here. Okay, so first template is that is the class, that is a type. Okay, second one is the template, that is the patch field. Okay, and third one is the geomesh. Okay, so why this there are 3 template is given, I can give you some just a simple example. But okay, so this class type that is written here, that is generally that what kind of variable you want to access. If you have the vector type of variable you are implying, or if you have a scalar type of variable implying, that things you can specify here. Okay, now this template, that is the template class patch field, this is another template whose definition will be given somewhere else. Okay, so generally this patch field, this I'm speaking about this patch field, that is the where you want to specify that what kind of the boundary condition you want to apply. So this the definition of this template will be should be defined somewhere else independent of the definition of the geometric class. So that is why it is written like this. Okay, because the definition is defined which is independent of this class geometric field. Okay, so here generally that what kind of the boundary patch you want to specify, that things here you need to specify here. Now the last one is the geomesh. So generally this template, that is the third one, that is generally related to the what type of the uh, discretization method you are going to imply, that thing generally it is works here, it carries here. Okay, so there are 3 template you can see with the definition of the geometric field. Okay, now it has been derived from the dimension field. Now dimension field has a one quality that if you want to apply any formula or any calculation using some definition in the solver, then it is not going to affect the boundary fields. Okay, so this is the quality of the dimension field. Now if you are deriving this dimension field in the geometric field, then it is obvious that the quality has been also copied into the geometric field. Okay, it means that if you are going to apply any formula to the geometric field, by default it is not going to apply to the boundary field. It is going to only change the value of the center cells of the given mesh. Okay, so this property is coming from the, because we are deriving this dimension field. Okay, another quality is also that it is going to work on the best of the dimension provided by the user. So it means that if you want to solve the velocity, the right hand side of the given equations have the same dimension to the left hand side of the given equation. So this two quality from the dimension field has been automatically derived into the geometric field. So you can see here that I have mentioned here that apart from the unit specification, another property of the dimension field is that it allows by default any arithmetic operation executed on any instantiation of the performed excluding the boundary condition. So it will exclude the boundary condition if you want to apply any arithmetic operations. Okay, so this is the capability of the dimensional field. So therefore it will also apply to the geometric field because we are deriving the dimensional field. Okay, so this what I have told you, that also I have again written here. So any arithmetic operation performed on the geometric field will exclude the boundaries of the domain. So that reason is that because the boundary values you always want to update using the some boundary condition. So the equation will solve only the internal cells. Now whatever the boundary condition you will applied on the boundary patches, okay, like no slip walls or inflow or outflow condition, that will be applied to the boundary patches. So that is why this geometric field don't solve for the boundaries when you are going to do any arithmetic operations. Okay, so for example, if you write v equal to v plus 1, so velocity equal to velocity plus 1 you want to solve. If you put this equation in your solver, it is going to only update the value of the central cells. Now if you want to change the value of a boundary patches, then you have to specify some boundary conditions. So this is the meaning of these two lines. Okay, now sometimes it happens that accidentally you change the value of the boundary field. Okay, sometimes it possible that you applying some equations and accidentally you also change the value of the boundary patches, and which you have not given as a boundary condition in the zero folder. So this is also possible. So there is one function that is the correct boundary condition. So if you call this function after that, then it is going to reset the boundary values whatever the boundary condition you have applied in the zero folder. Okay, so if you go to the source code, okay, so you can search this. So you can see here that this is the definition of the correct boundary condition. So if by mistakes you have just modified the value of the boundary patches also, and that is not matching with the boundary condition you have provided in the zero folder, in such situation you can call these functions, and this function will correct the boundary condition based on the boundary condition provided by the user. Okay, now if you go to the Linux terminal, you can find this correct boundary condition in almost every solver. Okay, so let me show you. So let me allow to go to the this foam solver folder directly. So if I type foam solvers, okay, so I am in the foam solver folder. Now if I find this function, so if I type enter, you can see that almost every solver has this correct boundary condition function. Let's understand that how this geometric field and the internal field has been defined in the geometric field, and how you can access the geometric internal field and the boundary field in the geometric field. Okay, so let's start with the boundary field. So boundary field is a itself a nested class. So what is the nested class? So if you are define a subclass within a given class, then it is called as the subclass. So boundary is a subclass of the geometric field, and the geometric field stored the boundary field as a private attribute. Okay, so what is the private attribute means that it can be only accessed and modified within the geometric field only. Okay, so it cannot be accessed or modified out of the geometric field class. Okay, so if you are creating one object of the geometric field, then by using that object you can only access the boundary field. Okay, because it has been defined as a private attribute. Now why it is important? So it is essential because you want to ensure that boundary values are updated correctly according to the boundary condition which has been specified in the zero folder, and it should not be corrected accidentally. Okay, so from out of this geometric field class you don't want to access the value, or you don't want to update the value of the boundary fields. That is the why it has been declared as a private attribute. Okay, now let's see the source code for the same things that what has been written in the source code. So this is the geometric field source code. Now if you go here, so you can see that the definition of the boundary is start from here, and it is defined within the geometric field. So this is the geometric field, and within the geometric field you are defining the definition of the boundary class. Okay, now here some private data is given in the boundary class. Here some constructor are given. Okay, some member functions are there. Okay, some operators are there, and here the definition of the boundary class has been ended. So these are the definition of the boundary class, and it is the subclass of the geometric class. That is why it is called as the nested class. Now if you see, the attribute of this class has been created in the geometric class as a private. Okay, so this is the private data of the geometric field. Okay, so for the geometric field, again you are giving some variable, creating some variable, and out of those variable this boundary field is a private attribute. Okay, so this is the private attribute. Okay, so this cannot be modified out of this geometric field object class. Okay, however, if you go little bit below and if you see some member function of the geometric field, you can find that there are two functions. Okay, so this is one function and this is the another function. Okay, so second one is the constant reference to the boundary function. Okay, so this is the constant reference to the boundary function. So what is the constant reference to the boundary functions? So here you can only access the values of the boundary field or boundary just to read. Okay, so here you cannot modify the value of the boundary field. You can just read and write the value of the boundary object we have created. Okay, so this is the constant reference to the boundary field. Now here you can see that this is the non-constant reference to the boundary field. Okay, you can see that this is the non-constant reference to the boundary field. Now it means that you can update the value or you can modify the value if you use this function. So this non-constant reference function, you can modify the value. So this kind of non-constant reference to the boundary field and to modify the boundary field values are generally required when suppose you want to use some thermophysical model. Okay, so using some thermophysical model, you are changing the some properties, and based on those properties or based on those conditions, you want to change the boundary field also. Okay, so in such condition, you are going to use this non-constant reference to the boundaries. Okay, so using this non-constant reference boundary, you can just modify those value, and I think that is why there is a reference is given. Okay, so this reference means that calling the reference of the boundary those you have created, you can change the or update the value of the boundary. Now, speaking of internal fields, so internal fields is directly inherited in the geometric field because we are using the dimension field. Okay, and the definition of the internal field already has been given in the dimension field. That is why there is no need to create a different object like the boundary to access the internal field. Okay, so here you can find a non-constant reference function similar to the boundary, that is the ref, that is used to access the value of the internal field and used to do the modification of the internal fields. Okay, so the difference between the boundary, that in the boundary situation you have to create one subclass in the geometric field, and then you have created the non-constant reference to the boundary field. But here it's because we are deriving the dimension field and already the definition of the internal field has been given in the dimension field, so we don't need to create another object for the internal field. Okay, so this is the definition that is given in the first comment. Now in the second comment you can see here that there is a function that is the ref, and similar to the boundary field you can give the non-constant reference using this function, and using this function you can modify the internal field value and you can perform the whatever the arithmetic operation you want. Okay, now if you go and see the definition, so that reference of this given to itself using this keyword, that is the star this. Okay, so using this star this keyword you are accessing the value of the internal field using the ref function. So let me go to the source code and show what I want to clarify here. So this is the geometric.h header folder, and if I go to the search for the ref function, okay, so here you can see that this two member function, that is the responsible for the accessing the internal field. So here you can see that is the reference to the internal field, dimensioned internal field. Okay, you can see that the definition has been written here. What is the this function? So here you can also see that is the reference given to the internal. Okay, now here you can observe that there is a constant reference to the internal field, and this constant is given if you want to just read the value. Okay, so here you cannot do the modification. So these two functions are used to access the internal field. Okay, now if I want to go to the .c folder, okay, so let me go to the .c folder, and here if you search ref, so here you can see that this is the method that you are returning the internal field of the this given mesh. Okay, so using this keyword start this, you are returning the value of the. So here you can see that to access the internal field, this internal field is giving reference to itself. Okay, so this star keyword is reference to the given object itself. So this is all about the how you are accessing the boundary fields and how you are accessing the internal fields. So before going further, we should understand this structure of the geometric field. Then you can correlate the different things while we are going to develop the boundary conditions. So you can see here that everything starts from the geometric field. Now this geometric field composed of the boundary field. So remember here, this is the geometric field class is given in the older structure of the OpenFOAM, but in new structure this is just a boundary. Okay, now this geometric field is composed of the boundary field, and you can see that this field is being derived in the boundary field. Okay, now what is the field? Field is a collection of boundary fields. Okay, now this is the patch field, that is the template class that is used to call the fvPatchField. Okay, so you can find this patchfield template class in the definition of the geometric field. So this is the this is the type for the if you are taking the different kind of mesh structure. So for example, you can call the volumetric mesh, that is called the FB mesh, and you can call the point mesh, that is called the point mesh, and its third one is called the surface mesh. So this patch field based on the given template type like FB mesh or point mesh or the surface mesh, this patch field will changes. Okay, so for example, if you're calling the FB mesh, then this will become the FB patch field. For point mesh, it will become the point patch field. Okay. Now there are different functions that are important if you want to understand that. You can see here that this. So I am going to just give you example for the FB patch field. Similarly, you can find for the point patch field. Generally, there is only two kind of patch field you can find. That is the point patch field and the FB patch field. So I am going to just explain about the FB patch field here. So you can see here that these two functions are the part of the geometric field also, and this is also part of the patch field also. Okay. So let me give you some summary from the starting. Geometric field is containing the internal field as well as the bounded field. Okay. So why it is important that this internal field and boundary field is not separated from each other. This should be part of a geometric field, because if you want to update the values of the internal field, then also you are going to require the call the values from the boundary field. And even if you want to use a different boundary condition, you will need to require the use the value of the what you can say the internal field. So that is why you cannot separate these two, internal field and the boundary field. And another thing is that sometimes it happens that you want to split the meshes, you want to refine the meshes. So if you are refining the internal mesh, then you need to refine the boundary field also. So that is why you cannot separate here. So this is the geometric field which provide a same platform for the internal field as well as the boundary field here. Now this FB patch field contains generally the boundary field only. Okay, so that is why this patch field is calling. This patch field can be of different types like the point patch field or the FB patch field. Okay. Now this is the class, that is the boundary field class, that is taking this FB patch field or point patch field, and it is going to use the evaluate function and update coefficient functions. Okay, so the definition of these two functions you can find in both classes. Okay, so let me go to the source code, then you will understand in more details. So here you can see that this is the geometric field.h. Okay, so let me go to the evaluate function. Okay, so this is the evaluate function. If I open, so here is another .c folder you can find, and the definition you will find on this .c folder. So let me show here. Okay, so you can see here that this is the definition of the evaluate function here. Okay, so here you can find two functions that is important, that is the init evaluate, initiation of the evaluation, and second one is the evaluation. Okay, so initiation of evaluate, it will take the values of the 0 folder, that is the initiation, and it is going to update. If it has been not started from the 0 folder, then it will first going to start from the 0 folder, and then here you can see that it is going to call the evaluate function if it is being updated for the initial conditions. Okay, now this definition of initiation and evaluate, you can find the FB patch field. Okay, so if we call this evaluate function here, so here you can see that initiated evaluate and evaluate function is given. The definition in the FB patch field is given here. Okay, so you can correlate here that these functions are also given in the geometric field and also given in the FB patch field. Now the second function, that is the update coefficient function. So let me just search update coefficient. So here you can see that the definition of update coefficient is given in the .c folder. So here you can also search the update coefficient. You can find here that this is the definition of the update coefficient. Okay. So here you can see that the difference between the evaluate and update coefficient, one difference you can find that here you cannot using the parallelization. Okay, so here you are just iterating over the every patch of the given boundary field. Okay, so this star will the define for a given boundary field, and it is iterating over the every patch of the given boundary field, and this operator is being used to update the coefficient of a every patches. Okay, so this is the definition of the update coefficient. Okay, now you can see that here the function of evaluate is very longer compared to the update coefficient. So why this is longer and this is very shorter? One reason is that because in update coefficient, whenever you are going to call the update coefficient, it is going to update the value of the given patch. But in the case of this evaluate, it will first check that whether evaluation has been done or not. Then if it is not being done, then it is going to evaluate the given patch field. Okay, so this is the difference. Also here you can template class find that this is the patch field where this fb patch field concept is come. Okay, so when you take the fb mesh as a value mesh, then it is going to become the fb patch field. If you are going to take the point mesh, then it is going to point patch field. Okay, so these are the different member function that is very important, that is update coefficient, correct boundary condition, and last one is the evaluate functions.